All right. In our last two examples here, we are going to do a division induction proof, and then we're going to look at a simple way to mess these up, right? So there are several different kinds available in the book, right? There's one about the harmonic series, there's one about sets, there's one about algorithms, right? There's a weird one about pi that's kind of interesting. Pie as in the food pie. That's kind of interesting as well. If you are interested in learning more about these or you need a little bit more practice, there's plenty of examples there. Um, I believe there's even a few worked examples in the extra examples PDF. So we will start by talking about our proposition. All right, oops, hang on, I need to get the pen reattached. Let's see, so we want to know that P of n is the proposition that n to the third divided by n is divisible by 3, right? When n for n is a positive integer. Right, so that's, sorry, that's the weird fancy n. That's the fancy set that we've learned. So we want to consider first our basis step. Our basis step in this case is P1, right? Because we're interested in n in the natural numbers. So B is 1. And we know the P of 1 would be that 1 to the third minus 1, not n. That is 1 to the third minus 1 equals 0. Is that divisible by 3? Yes, is divisible by 3. So that completes our basis step. And then we want to consider our div step. So what is our inductive hypothesis in this case? We assume that pk is true. We are assuming that k to the third minus 3, oh, k to the third minus k is divisible by 3. Right, for any arbitrary positive integer k. So what do we want to show? We want to show that pk implies pk plus 1, where pk plus 1 is that k plus 1 to the third minus k plus 1 is divisible by 3. Alrighty. So what do we need to do here? We can look at k plus 1 cubed minus k plus 1. Right, so that is equal to cubing it out, k cubed plus 3k squared plus 3k plus 1 minus k plus 1. And if we do a little bit of algebra, then we have that k cubed minus k plus 3k squared plus k. Where's that coming from, right? We have k cubed minus k, 3k squared is here, 3k is here, and these are just plus 1 and minus 1, right? So we have that is equal. And what do we know? We know from our inductive hypothesis that this is divisible by 3. Great, cool, that's nice. We also know that this is multiplied by 3, right? So if this is divisible by 3 and this is divisible by 3, and we add them together, right, then we get right? If we add together two things that are divisible by 3, the result is divisible by 3, right? So therefore, k plus 1 cubed minus k plus 1 is divisible by 3. I do apologize, my handwriting on the tablet is not great, but we've got that. We're good to go. Right. Alrighty. So this is a fairly common mistake, particularly because the basis step is so simplistic so often, right? So what's happening here? We are going to pretend that we just kind of forget to do the basis step. And we're going to prove something that is obviously not true, right? So P of n, the proposition, is that the statement is that n is equal to n plus 1. So our inductive step, induction step, is that pk is true. We're assuming that this is true, which means what? Which means that k equals k plus 1, right? So then what do we want to show? We want to show that k plus 1 is true. Here, yeah, this is our goal, to show that this is true, which means we want to show that k plus 1 is equal to k plus 1 plus 1. Put some parentheses on there. This is our goal. Well, what do we know? We have that k plus 1 is equal to, or k plus 1 plus 1, right? So this is using our inductive hypothesis, right? Because our inductive hypothesis is that k is equal to k plus 1. Right? So this is a very simple, and obviously very incorrect statement. But part of our induction step is that we are assuming this is true. Right? And if we are assuming this is true, this is our inductive hypothesis. Well, k is equal to k plus 1. We are saying that that is true. Therefore, we are showing that k plus 1 is equal to k plus 1 plus 1. Therefore, we have shown. Right? So what this is supposed to, this silly example is pointing out to you is what? Think about it. Take a second, pause the video, try and predict the point I'm about to make. This is pointing out to you that the basis step is important, right? The basis step is important in the sense that if you don't do it, you may be able to do the inductive step, right? You may get that domino k knocks over domino k plus 1. But you have to show that domino 1 is true, right? Can be knocked over. You have to show that domino 1 is even there, and it can then it knocks over domino 2, and so on, right? This step is great and it's important, but you cannot do it without showing that this is true and it's there, right? And obviously this is a silly example, but there are much more complicated examples where if you look at the inductive step, you can show, sure, you can show that if you have this for k, it is true for k plus 1. But if you don't do the inductive step, or if you don't do the basis step, you're wrong, right? There's no proof there. This is obviously not true. But we've just shown that it is by forgetting to do the basis step in the first place. There's a more complicated one in the book that I like that's talking about how if you have non-parallel lines in a plane, right? X number of parallel lines in a plane must, or non-parallel lines in a plane must all equal, or must all meet at a point, at a common point, right? Um, I would suggest you take a look at that. It's an example of how you can kind of get caught up in the inductive step, and you can very, very easily miss the choice of B, right? So this is also an interesting note with the choice of where your basis step is. All right, so I hope you guys are ready to start with strong induction on the next class, and I will see you then.